1, Units of Measurements. In this chapter, we're going to cover the following topics: SI English Units System, Conversion of Units, and Per Unit Measurement System. SI units have the following features. It's a decimal system. It employs many units commonly used in the industry and commerce. Examples are volt, kg, and watt. It is a coherent that expresses with simplicity some of the most basic relationships in electricity, mechanics, and heat. Following are examples of SI used in electrical machines. For mechanical quantities, we have angle in radian, energy in joule, force, Newton, mass, kilogram, power in watt, and angular velocity in radian per second. While for electrical and magnetic quantities, we have frequency in hertz, inductance in Henry, magnetic flux in Weber, magnetic field intensity in ampere per meter, magnetic flux density in Tesla, electromotive force in voltage, and magnetomotive force in ampere turns. The symbol of each quantity can be seen written on the right hand side for mechanical and for electrical and magnetic. While on the right hand side of the table, we have the symbol of each SI unit. The scale conversions in SI units, we usually use the following prefixes. For example, if we have 10,000 volt, we usually write it as 10 kilovolt or 10 times 10 power of 3 volt. So keep in mind, you may write down your answers in the following prefixes. The conversion of units. The following are some of the commonly encountered quantities in electrical machine. Length. If the dimension is given other than the SI unit, example, if you're given 100 centimeter, you need to change it to 1 meter, then only you can start your calculation. If it's given in 1 millimeter, you have to convert it to 0.001 meter or 1 times 10 negative 3 meter. For power, which is usually expressed in horsepower, we need to convert it to SI unit kilowatt to do our calculation. For 1 horsepower, it's approximately 746 watt. Unit of conversion can be done by using your scientific calculators, which you can refer to the back of your calculator or the cover of your calculator. You can use the command Shift 8, which is the conversion command, followed by the number 0.01 to 40. If you want to convert horsepower to kilowatt, you may key in number 29. For velocity, usually we will change units from radian per second into RPM or revolution per minute, or vice versa. We will see the conversion of units for velocity in the DC machine chapter. Next, per unit system. An SI unit specifies the actual magnitude of any quantity. For per unit system, it is a system or number which enables us to have a better idea of the size or ratio of something by comparing it with the size of something similar, which normally we use the base or nominal value. The formula to find the per unit is given as the actual value divided by the base value. Hence, it is a ratio, which you can also express as the following equation. There is no actual SI unit for this as it is in ratio. For example, if I have R1 equal to 10 ohm and I have the base value which is 15 ohm, to find out the per unit of this resistance, I need to use the actual value divided by the base value. Both in ohms will cancel each other and give me a result which is in ratio of 2/3 per unit. Advantage of using per unit system, it simplifies your power calculations. It provides an easier way to access the conditions of entire system without verifying the specific nominal voltage or value of each subsystem, especially if you have a very large scale system with many nominal values. It also narrows the range, makes it easier to identify incorrect data. Most of the power flow analysis software requires your input or reports the result in per unit. Per unit with one base example. 3 motors have power rating of 25, 40, and 150 horsepower. Let us select an arbitrary base power of 50 horsepower. Find the per unit for 3 motors. For our solution, first we are going to write down the given clues, which are the actual values of the motors, and also the base power. To find the per unit of each motor, we're going to divide the actual value of the motor's power with the base value. For motor 1, 25 per 50, motor 2, 40 per 50, and Moto 3, 150 per 50. From the result, we can see that Moto 3 is 3 times higher compared to Moto 2 and Moto 1. Another example of using per unit with one base value is converting a conventional circuit to a much readable per unit circuit. 1500 ohm is used as the base value. R1 from 3500 is converted to per unit by dividing the actual value with the base value, followed by R2 450 divided by 1005, inductance 4800 divided by 1005, and the capacitance 3000 divided by 1005. From the per unit, we can conclude that the inductance has the highest impedance, followed by R1, and then the capacitance, and lastly R2. Next, per unit with two base value. In electrotechnology, the per unit system becomes particularly useful with two bases involved. They are usually voltage and power. With this, we can also establish other corresponding or related values such as current and impedance. To find the current base value, we can use power divided by voltage. After that, we can substitute into Ohm's law to find the impedance, which is voltage divided by current. Example of using two base values to find current and impedance. We are given the base power 500 kilowatt and base voltage 4 kilovolt. To find the base current, we need to divide the power over voltage, which is 500 over 4. We get 125 amp. To find the base impedance, we need to divide the voltage over current, which is 4000 divided by 125. We get 32 ohm.
Okay, finish with the unit of measurement. Let me look at your tutorial first. Because if I continue with the lecture video, you might fall asleep. Let me find the tutorial first. For unit of measurement, actually we're going to use it in the lab report. Unit of measurement is useful when you want to plot graphs. So for tutorial 1, you can see the screen. The first question is just about definition. So what you're learning here is the electrical machine. If you want to find books, you can either type in electrical machine or electromechanical energy conversion. Okay, some of the book titles they are defined according to this. So electromechanical just means that is a machine lah. Okay, it's powered by electricity. We have electric, okay, and then we have mechanical movements. Okay, the electricity is converted to force or torque. So that is mechanical. Okay, energy means we are just supplying power through the motor or the generator. Okay, we can supply power or we can supply force or the torque, the mechanical energy also. So conversion is change lah. Okay, so we are changing the electrical to mechanical or mechanical to electrical. So if you want to find related books or material, you can also type in these 3 words here. If not, you can like go to the library website. You can just key in electrical machines. If you want to find books, that's how you find. Just type the subject's name. Question 2 is just a revision. Okay, just use Ohm's law lah. Okay, in electrical, usually we denote the voltage or the source as E rather than using V. Okay, if you look at electronic books, they usually use V. Okay, so if for machine, because they will generate the electricity, so we call it electromotive force. That is the name of the voltage. Right. Voltage is a unit lah. Volt. So if you put it as E, usually is for power systems. For electronic, you can see that your lecturer will usually use V rather than use E. Depends. Okay, so you have 400 ohm. And this means this is your rating. Okay, or the true value lah. Okay, this 6. Oh, sorry, rating is actually your base value here. This is your true value, 400 ohm. So you write down what is given. Then 60 amp also is your actual value. Okay, these are actual values. Then you're given the base voltage. Okay, usually this just now I mentioned is your rating lah. Okay, rating is used as your base voltage or base currents. Okay, so 4 kilovolt and the current is 125 amp. So they already mentioned this is base value. If not, usually we use the rating as your reference. Okay, base also means is reference, which you use in the calculation to find the per unit. So for this information, they ask you to find per unit resistance, per unit current, per unit voltage, Ohm's law lah, E equal to IR. And also you can find the power. Okay, and then you can find the actual voltage, okay, across the resistor and actual power. You just use the equation only. Okay, if I want to find actual, just multiply the per unit with base for this one. Okay, I need the actual value. Then if I have the base value, sorry, I want to find the actual value. I just need the base value times the per unit, okay, to get the actual value. So for the A here, first thing you do is actually write down the equation. Okay, when you write down the equation, you'll see that you have this R. But you notice that this is missing. So next thing you do is how to find this base value for the resistor. And you can use the Ohm's law lah. Okay, we have the base value for voltage and current. And using this, we can find the base value for resistor. So we substitute it in. Okay, if it's missing, find it. Okay, write the equation out first. After find, you can substitute it in. Then the answer here, there is no unit, unitless, because it's per unit is a ratio. Okay. Next thing is they ask you to find the current. Again, write out the equation. Okay, do you have the information? Yes. This one also yes. Straight away you can find the current. Next is the voltage. Since we already found the per unit resistor and the current, we can substitute straight away. This is already in per unit. So the next one is power. Okay, per unit power. So you can find the per unit power using voltage times current. Okay, again, it's in per unit. Okay, the last one is asked to find the actual value. So to find actual value, you have to use the base value times the ratio of the per unit value. Then you get back the actual value. Okay, this one, write down the SI unit here, 24 kilovolt. And power also, you do the same. Okay, we found the per unit. Okay, do you know the base value for power? This one actually don't know. We don't know this. So actually you can find using base voltage times the base current, which is given in the question. Okay, then also find this, multiply the per unit. Okay, you can find the actual value. Or we already find the actual value here. Okay, you already know the actual value of current. You can use this also. You will get back the same answer. Okay, rather than going through this. Okay. So the next question, they give you a figure. Okay, again, this is also revision for parallel circuit. Okay, they have a figure for you. Okay, the information given is the voltage source here. Okay, or the E. You have the two load which is connected in parallel. Okay, you have a resistor and a boiler. The boiler, they just straight away give you the power. These are actual values, all these three. And base value, okay, is, like I say, is a rating lah. You have a 4 kilovolt, then you have the base current. Okay, you have like EB, IB, just same as question 1 there. Okay, again, same like question 1, find the voltage, resistance, power. This power, they never mention which power. Of course, is the resistor power lah. Okay, the boiler already know the power. Okay, so I assume they're asking for the power across here, or the resistor's power. Already no need to find the power across the boiler. We already know that also. Okay, the next one, they ask you to find the I2 per unit and I1 or the line per unit. Okay, you can use Kirchhoff current law since it's going down here. Per unit power absorbed by the resistor. Sorry, this one I think is the boiler. P per unit. But the book never label properly last time, so assume it's P boiler lah. Sorry, because this one they asked to find the per unit the resistor. This one should be the D. Power absorbed by the resistor, this is the actual power. Okay. And the actual current of the line also is IL, actual. So again, write down what is given in the question. Okay, whenever you do test or exam or any other subjects. Because sometimes the question can be very long-winded. Some of the lecturers, that question may be like, you are an engineer at where, and you are trying to fix this and this. Okay. You might think that we are trying to make sentence or paragraph, but sometimes there is no choice. We are setting question based on what is required by the EAC lah. Okay, we have for auditing, and then they want us to set question like that lah, assuming you're facing a situation, okay, not just giving you question and solve it directly lah. That's why you see secondary school student, the question also is like, the math also is like English question. Okay, they don't straight away give you 1 + 1 = 2 already. They will say, you have an apple, then your mother give you another 2 apples, then your brother eat 1 more apple, right? But you're actually trying to solve maths. Okay, so it's better to write down what is given, just like how you want to solve maths. This is also what we learned last time. Last time we also used to get long-winded question. So you write down what is given first. Okay, another advantage if you write down is you don't make mistake. So voltage given is this value, you write down. Resistor is this value, you write it down in, okay, so that you don't have to look at the question again and again. So I don't have to read the question already. I have the information on the top here, so you can refer it. Or you can see what is missing also. Okay, 1, 2, 3, 4, 5. You have 5 information. If you are missing something, then you know you need to find it. Okay, per unit of the voltage source is, you have the actual voltage divided by the base. Straight away you get a per unit. Okay, nothing difficult there. This one is similar like the question 2. Okay, you're missing this, so find it first. Okay, of course you write this equation out first lah. Then you see this missing, then you find this, substitute in. Okay, for tutorial or for books, they know what is missing already. So straight away they find this, they substitute this in. But in a test or exam, what you do is first you write down the equation. Okay, then you find what is missing from that equation. If this is missing, find it. Okay, of course from the book, they already know what is missing, substitute straight away without, if you read without thinking, then during test or exam, you're stuck because you don't have a strategy to solve questions. Okay, so plan out a strategy lah. Then for the power, okay, since the question D already asked to find the per unit power of the resistor, so I assume this is power for boiler lah. Okay, straight away you have the power at the boiler, substitute in the base power, current times voltage. Again, write out the equation, see what is missing. Okay, then find and substitute it in. Current at I2 is, you can see you can use Ohm's law. Okay, since it's parallel, voltage is the same. Okay, we already know the per unit voltage. And the per unit resistance we found, then just substitute in. You will get the current at the resistance side per unit. Okay, then to find IL, you have to find I1 first. Okay, again, write out the equation. Okay, this is missing. Don't know this, so you have to find first. This one you already found. So I1 is at the boiler side. You already know the per unit power at the boiler. Just use the power equation, divide by the voltage, you get the current. So just substitute in. Power at the resistor, okay, we already know the voltage per unit. I2 also we found just now. Then you can find the per unit power at the resistor. And again, to find actual power in watt or kilowatt, you use the ratio or the base value. Sorry, per unit is a ratio. The base value or the rating here times the ratio or the per unit. This is at the resistor. Okay. So the power at the resistor and the actual current, the total current. Okay, we know the base current, we know the per unit. Okay, just put in, then you solve for the current. Of course, you can check your answer. Okay, for example, you can also find this actual current, I2, here. Okay, we know the actual voltage. You can always use another method to check the answer. Okay, checking. When you are in test or exam, you know there's another equation or there's another method to check your answer. Always check using different method. Okay, that is for tutorial 1. Okay, no any question on this? No question? Okay, so just now I mentioned the per unit actually is used to plot graphs. Okay. How do you want to plot graphs? Let's say motor lah. We are measuring the efficiency. Okay. Output over input. For motor, actually your output is fixed. Correct or not? But in the lab, we want to find the input, okay, or the efficiency is governed by this equation. The input is not fixed. Okay, input depends on the motor's construction, because even if you have resistance, okay, same like the resistance, if I buy a resistance, it says 5 ohm, this actually has to be 5 ohm. Okay, so because you label there 5 ohm, same like the motor. If I buy a motor, I buy 1 horsepower. This 1 horsepower actually means the output, right? Not the input. Users are not interested in the input. I buy 1 horsepower. This 1 horsepower have to have enough power to drive something lah, drive the load or something. If it labels 1 horsepower, but it only give me half 0.5 horsepower, you say, you're cheating my money lah. Just like you're buying a car. If your car is, you mentioned is 1 horsepower, but you only get 0.5, is you buy a motor, you buy a motorbike. You're not buying a car or whatever. You're buying a kanchi. Something like that lah. So the input depends on the car lah, or the motor also, right? So input depends. So we have to measure a lot of things. We have to measure the current, the voltage. Okay, this is input. If you have a DC motor lah, voltage, current. Then you need to compare the efficiency also. How to compare efficiency? You also can calculate lah. You get the output, divide by input. Okay, then let's say you want to plot this also. So there are so many graphs, 1, 2, 3, 4, 5. And then output also is governed by the torque, okay, and the speed. Okay, if let's say you want to plot this also, the torque and the speed. Okay, so how many graphs you will have? 1, 2, 3, 4, 5, 6, 7 graphs. Okay, if you want to give people look at 7 graphs by itself, can also. I plot 1 output like that. Then I have input like that. Then I have current like that against time, of course. So you have 7 different graphs. Of course, you can analyze one by one. But let's say I want to know what's the relationship of the current with the input power, or the current with the output power, or the torque against input power, or the torque against the current. So I want to plot them all together. If I want to plot them all together, but there are different units. Power in, let's say, kilowatt. This is so high, it's times 10 power of 3. Current, let's say you only have 1 amp, 2 amp. Okay. Or the maximum current is 1 amp. And then you have the speed also, you have the torque, different unit. If let's say I plot 1 amp and this is a kilowatt, you don't see anything. I want to plot current and power together. Let's say this is my power. And then my current is so small on the bottom here. This is kilowatt. This is in amp. I don't know even if this line is going up or going down. Cannot see anything because this range is too big. Okay. So one way, what do? I can actually divide this power output with a base value. This input power also I can divide with the base value. Current I can also divide with the base value. Okay, after you divide this with the base value, you actually get it within maybe 0 to, it can be over 1 lah, okay. Because if it's greater than the base value, it will be over 1. If let's say it stays within the base value, it will be 0 to 1. Here also 0 to 1. Here also 0 to 1. So everything you can plot in one graph. Okay. So if they are all within the same range, okay, which is 0 to 1, that's the time, I can plot my per unit current, per unit power, the top, or if it's against top, then you don't have to plot the top. The speed, okay, if it's in the lab, you use the RPM, also in per unit. So all of this, you can see the relationship of the current, the power, okay, the speed, let's say, okay. So you can see how they relate to each other, okay, using one graph. Okay, this is the use of it lah. Another use is when you do programming. Okay, you use it as the base value for the program, or you use the per unit. Okay, so sometimes you don't want too big values in the programming, in your software lah. Okay, so you use base value also. Then after that, using software, you can also plot graphs in per unit. If not, last semester you guys took electrical power system or something like that, right? With Miss Yo. Like transmission lines, they all also use the per unit. Okay, to some of the equation, they also use the per unit. Tutorial 2 is for magnetism, which I think you guys also studied it before. Okay. Without magnet, the motor cannot move. Okay, so the electromotive force is the one that is moving the motor. That's why you need to restudy this again. Okay, it will be in that's why it's included in your syllabus. So we're going to look at chapter 2 now. I'm going to paste the link here, so if you don't want to see from my computer, you can also see from your own computer or your handphone.
Fundamental of magnetism. In this chapter, we're going to cover the topics, magnetic quantities, laws, and concepts, hysteresis and eddy current losses, Faraday's law, and Lorentz force. Magnetic fields are fundamental mechanisms by which energy is converted from one form to another in motors, generators, and transformers. Figure 1 shows a basic magnetic core structure. Number of windings are wound across one of the legs of the magnetic material, and current is supplied through the winding to form a magnetomotive force. These will form flux flowing inside the magnetic core structure. The magnetic material has a reluctance R. The magnetomotive force is given as Ni. N stands for the number of turns of wire in the coil, and I is the current. The SI unit is ampere turns. We can also use Ohm's law of magnetic circuits, which F equals to flux times the reluctance. These are analogous to voltage equals to current times impedance. Hence, we can write flux equals to F over R, in which the flux is analogous to current, magnetomotive force analogous to voltage, and the reluctance is analogous to the resistance. Permeance is the inverse of reluctance, hence we can write as permeance times the magnetomotive force N times I. Unit for flux is Weber. An example, what flux is in a core that is wrapped with a 300-turn coil having a current of 100 milliamp if the reluctance of the core is 1.5 times 10 power 7 ampere turns per Weber. We are given the number of turns of coils and the current and the reluctance of the core. Hence, to find the flux, we just need to substitute F over R, in which F equals to N times I, 300 times 10 power negative 3 divided by the reluctance, 1.5 times 10 power of 7 to get 2 microweber. Next, we have mu R equals to the actual mu divided by mu naught. This, as you can see, is a ratio, hence it's unitless. Mu R stands for relative permeability, which is the ratio of the absolute permeability to the permeability of a vacuum. The permeability mu defines the ease with which a magnetic field can be established in a given material. In electromagnetism, it is the degree of magnetization of a material that responds linearly to an applied magnetic field. The permeability vacuum or free space, denoted as mu naught, is given as 4 pi times 10 negative 7 Henry per meter, which is used as a reference or base value. You can find this value from the scientific calculator, constant number 33, which is exactly equal to 1.2567 times 10 negative 6. Hence, we can use the permeability to find the reluctance, which is equal to length per mu A. The reluctance is defined as the opposition to the establishment of a magnetic field in a material. The reluctance SI unit is given as ampere turns per Weber, in which you can also derive the SI unit from the magnetic Ohm's law, in which F equals to flux times the reluctance. Hence, the reluctance is equal to the magnetomotive force divided by the flux, in which we will get the unit ampere turns per Weber. The length, which is the path of the magnetic flux, is in meter. The permeability, Henry per meter, and the area of the core is in meter square. Magnetic flux density is the amount of magnetic flux in an area taken perpendicular to the magnetic flux direction. The magnetic flux density SI unit is Tesla, and the flux is in Weber while the area is in meter square. We can also write the SI unit as Weber per meter square. From figure 3, we have 1 Weber of flux crossing through a 1 meter square area. So this one will give us a 1 Tesla of magnetic flux density. Magnetic field intensity is the ratio of the MMF needed to create a certain flux density within a particular material per unit length of that material. The magnetic field intensity, as shown in the equation, we can write the SI unit as ampere turns per meter. The F stands for magnetomotive force in ampere turns, while L stands for average length of the conductor's path in meter. And we can also write the equation for the magnetomotive force as number of turns times the current. Example, find the magnetic field intensity at the circle. We know that the length of the circumference is 2 pi r. The radius is given as 5 cm as shown. So to find the magnetic field intensity, it is F over L. We know the number of turns of the wire, which is 1, and then the current is given as 50 amp, while the length is 2 pi r. Changing from centimeter to meter, we get the magnetic field intensity as 159 ampere turns per meter. In free space, the magnetic field density is directly proportional to the magnetic field intensity. which we can write it as B equals to K times H. This constant is called the permeability constant or mu naught. It is the constant for the proportionality of free space. Hence, we can write B equals to mu naught times H. Figure 4 shows the relationship between the BH curve in free space, which is linear. The linearity from the graph gives us the equation. We can write H equals to approximately 800,000 times the magnetic field density. The 800,000 is taken from where the mu naught is 1.26 times 10 power of negative 6. If we inverse, we will get approximately 800,000, in which H equals to 1 over mu naught times B. The linearity is only true for free space, while non-linear relationship, as shown is in figure 5, shows the BH curve for magnetic materials, in which their relative permeability is a non-linear constant. Hence, we can write the magnetic field density equals to mu H, in which the actual permeability can also be found by multiplying permeability of free space with the relative permeability mu R. In figure 5, we can see silicon iron has a higher density compared to cast iron, and the free space has a very low magnetic field density. Magnetic materials will saturate at a certain level, in which this characteristic is reflected in the DC or AC machine.
Okay, the next video is at chapter 2B. Or you guys want to have a 5-minute break? Okay, we have 5-minute break. Then I'll come back after 5 minutes. Okay, it's been around 5 minutes. Is everyone back? You can eat in front of your computer. That's the best of having online class. Even if not online, if my student bring in food from canteen, I also don't mind lah, because you're in a university lah. If you're in the DK, you can eat whatever you want also. I don't mind. But if you're in the tutorial room, it's a bit hard lah. I just want to go through the equations with you guys just now. It's steamboat in front of a computer. Until your computer got soup in the DK. Pay to get steamboat in the college. Don't have lah. I think the canteen all bankrupt already lah. No students are more. Poor canteen people. I don't know how they survive. Maybe don't have canteen already. Yeah lah. The one selling the rice, the economy rice, they've been there for like, before I went into college, they was there before me, the canteen. The boss of the canteen. 20 years. The canteen boss been working there for more than 15 years, I think, or 20 years. I don't know, although they look so young. You know the tauke of the canteen. They've been there more than 15 years, I think, more than that. Actually, this hatch intensity, we don't use much lah, okay? This hatch here in our calculation, because I don't really give, or the question in the book also doesn't use this much, okay? This one is just to tell you the response of the motor, actually, okay? This hatch, we don't use much, because as you can see, it's per length. Okay, if we solve the question like this one looks more like a transformer. Okay, so we're not dealing with one thin wire like this, actually, no. Although you see when we draw the equivalent circuit, it looks like a thin wire, but it's not a wire. Okay, it's just a representation for this core here, okay? Assuming, let's say you have the flux flowing, okay? It's just like a path, okay? Let's say you have a current flowing, okay? It's just like a conductor's path. It's not a thin wire, okay? It's a plate. Even if you look at this also, this is not a thin wire also. It's few hundred thousands of coils winding here, okay? So actually this equation, we don't use much lah. It's just for your, so this equation, we don't use it much, okay? It's just for your knowledge lah. This one, we don't use it much because it's for a certain length only lah. Okay. And we just want to show you this because for motor, you know why if we supply even more current to the motor, it cannot run the speed higher. It cannot go like that because it will saturate, okay? Because of due to this nature here. Okay, mu naught times mu r times h. If you have a conductive material, like silicon iron, cast iron, it will saturate at a point. Okay, so in the lab, you also see the motor run linear, then it will reach a maximum point. Okay, so depends on the ferromagnetic material that you see or you use. And let's say you're in a test or exam, then it asks you what are the type of material that is suitable as ferromagnetic material. Actually, you can Google it up. Okay, like this already got 2 examples here, silicon iron and cast iron. Okay, metal, if you just say metal, actually metal doesn't make a very good magnetic material. Okay, so before you answer a question, there is actually clues in the notes already. It's like silicon iron, cast iron. These are already the answer, ferromagnetic material. Okay, we are going to look at the next video, which is continuing. It's chapter 2b here. You can also play on your own. Okay, I will cast it here also, so I know when is it end. And then if you got any question, also you can ask here, but I think this is quite direct.
Circuit. We can use the analog of Ohm's law in electrical circuit into the magnetic circuit. Figure 6 shows the electric circuit and figure 7 shows the equivalent magnetic circuit, in which the magnetic flux is same as current and the MMF is represented as the EMF in the voltage source, and the magnetic reluctance is the equivalent of resistance. The magnetic circuit is analogous to the electric circuit as shown in the following table. Same law used in the electric circuit can be applied in the magnetic circuit. The table shows the representative in each of the electric circuit analogous to the magnetic circuit. Figure 8 shows a simple magnetic circuit in where a current is supplied to a winding on one of the magnetic core legs. The N and I will create a magnetomotive force F. And this enables the flux to flow inside the magnetic core structure. We can use the mean core's length in where we take the length as the middle of the core sections as the total length, and the area as the width of the core times the depth of the core. Hence, we can find the core's reluctance using the dimension
length over mu A, where the mu is the permeabilities of the magnetic core. If we are given the relative permeability, we can find the actual permeability by using mu naught times mu R. From the flux, we can relate it to magnetic field density times area, where the magnetic flux density can be found by dividing the magnetic flux to the area. Change the dimension of the magnetic core structure into an equivalent magnetic circuit. We can represent the windings of the coil as a source. How do we determine the polarity of the source? We can use our magnetic field right-hand rule, in which our fingers will coil according to the direction of the current flow inside the winding, and our thumb indicates the flux direction, in which it flows from negative to positive, following the direction of our thumb. Hence, we can represent the winding using the source. To complete the equivalent magnetic circuit, we are going to label the length of each core as shown. L1 will represent the left of the core, L2 the top, L3 the right, and L4 bottom of the core. Area of each core will be their respective width times the depth. Area 2 will be the top core's width times the depth. Area 3, the width on the right times the depth, and the area 4 will be the bottom core's width times the depth. The reluctance can be found by dividing the length with mu A. Since the reluctance of the core are connected in series, the total core will be R1 plus R2 plus R3 plus R4. And the core will be connected to the MMF source. If the denominator of the equations of the series reluctance is the same, we can simplify, become length of the core divided by mu area of the core. Since the area is the same and the mu is the same, the length will be the total length 1, length 2, length 3, and length 4. For parallel structure, we can use the parallel circuit equation to solve for the reluctance. As inverse of RC will be equal to inverse of R1 plus inverse of R2, and so on. Consider the magnetic circuit with an air gap of the length as shown in the middle of one of the core's legs.
As the flux flows through the air gap, the magnetic flux line will bulge outward. This increases the effective cross-sectional area of the air gap, in which is known as fringing field effect. If the field is neglected, we will assume the area of the air gap is equal to the area of the core. For a magnetic core with air gap, we can see that if the air gap is in series with the core, we will connect the reluctance of the air gap as shown. And since they are in series, we have the flux of the core equal to the flux of the air gap, in which is equal to the flux total. The equation for this circuit will be the MMF equal to the R total, which is R core plus the R gap multiplied with the flux. Calculations of the flux in a core performed by using the magnetic circuit concepts are approximations. It's around 5% of the real answer. This is due to the following reason. Number one, we assume that all the flux is confined within the magnetic core structure, which this is not true. A small fraction of the flux escapes from the core into the surrounding air. This is called the leakage flux. Number two, the calculation of reluctance assumes a certain mean path and the cross-sectional area of the core. For the path length, we only consider from the middle of the core and not the longest or the shortest length. Well, number three, in ferromagnetic materials, the permeability varies with the amount of flux already in the material, but in our calculation, we consider it as a constant. And number four, sometimes the area will increase due to the fringing field effect of the air gap. While in our calculation, if we neglect, we might assume that the area of the air gap will be equal to the area of the core. Kirchhoff's voltage law and current law can also be applied to solve the magnetic circuit. As stated by KVL, total MMF supply will be the total MMF consumed, while KCL, total flux flowing inside a junction, will be equal to the flux flowing out of the junction. While all electrical DC circuit analysis techniques, such as mesh analysis and nodal analysis, can also be applied in the magnetic circuit analysis. Figure 13 shows a magnetic core with a T-joint with two supplies. As can see, we have I1 flowing in the coil N1 and I2 flowing to the magnetic winding N2. Assuming that the magnetic core structure has a infinity permeability, hence the reluctance of the core will be 0, or it will be neglected, and we will left with the reluctance of the air gap as seen. From the diagram, we can draw the equivalent magnetic circuit as seen from the coil N1. Using a right-hand rule, flux will flow from negative to positive in this direction. Hence, we can write the MMF F1 by representing it with a source. And F2, using your right-hand rule, the flux flows down as shown, and the negative positive direction. We can draw the equivalent source. For the flux flowing inside the coil, we have flux 1 on the left hand side through the gap 1. We can represent the reluctance of the air gap as series with the MMF F1. And next, we can see the flux flow to a junction when it is split to flux 2 and flux 3. For flux 2, it is at the right-hand side of the core, and we can represent the air gap reluctance, which is connected series with MMF F2. While on the center of the core, we have the air gap 3, in which it is parallel to F1 and F2. Hence, we have the equivalent magnetic circuit as shown. We can use a mesh analysis to solve for this equivalent circuit. We have loop 1, in which we label the flux direction clockwise. Next, we will label the polarity of each reluctance in this loop, following clockwise direction. On the second loop, we will also label the flux direction as clockwise, and also label the reluctance polarity based on the flux direction. Next, we will write the loop 1 KVL equation. Following the flux clockwise direction, the flux is flowing out from the source. Positive F1 minus flux 1 times air gap reluctance 1 minus flux 1 times air gap reluctance 3, while flux 2 is flowing out. positive of A gap 3. Next, for equation KVL for loop 2, we have the flux 2 flowing out from F2 as positive, flowing out of A gap 2 as a negative, and A gap 3 also negative. While flux 1 is flowing out from A gap 3 at the positive end of the reluctance. Hence, we have these two KVL equations which we can solve simultaneously to get either the value of flux 1 or flux 2. If we are given the MMF values and also the reluctance values. We can also write the KCL equation as flux 1 equals to flux 2 plus flux 3 in this junction.
Okay, we finish with part B here. The important thing is to draw the equivalent circuit. Is everyone back? Finish watching the video? Or you just sleepy already? If I were to teach new subjects, I will not have the time to do this type of lecture video again. And then, as you know, we don't have a script to read, right? And when I do this video, I was talking very slowly. Okay, one is because whenever we have class, the student always comment that we talk too fast. Okay, but if after I record video, one thing good about YouTube is you can fast forward it, right or not? When we record a video, you can like fast forward it, you can make it faster, or you can even make it slower. It's good about the video. And one video take around half a day just to edit, to redo. If we say something wrong, we have to record again. Anyone is a YouTuber here? No? If you're a YouTuber, you know how difficult it is to do a video. Or you have an assignment, you need to do a video for presentation. How many cuts you need to take? For the important part in this, you need to use Ohm's law also lah. Okay, it can be used in magnetic circuit, as you can see here. Okay, F equals to flux times reluctance. Then you can also use mesh analysis, nodal analysis. I prefer mesh analysis, okay, because nodal is I think nodal is a bit more steps. You need to see all the nodes, all the current flow in or flow out, that you make more mistakes. For magnetic circuit, besides representing using voltage, some of the book they also represent using current source. Okay, because some of them you can do nodal analysis if you want, but I'm using this book which they use voltage source. Okay, although this one the unit is in ampere. Okay, because of the formula, number of turns times current. The unit for this is actually ampere, but you see the symbol that they use is voltage source rather than current source, because I think they prefer to use mesh analysis. For me, mesh is easier, okay, rather than using nodal. You can use nodal also, okay, but I think nodal you tend to do more mistakes. So if you stick to one method only, if you want to use the other method, you are also correct. Okay, let's say you're drawing the equivalent circuit like this. Okay, if you look at this, it's hard to visualize. If we want to solve using this 3-dimension diagram is a bit hard. Okay, so simplify it with a circuit. So we're drawing this winding as a voltage source. If you draw it as a current source, also can. This is also correct. Okay, I also give you correct. This is also correct. So both is correct. Okay, as long as you know that this is a source. And draw the source means that either is a current source or a voltage source. I've seen some of the students, maybe they're lazy, they just draw a circle like that. If you draw a circle, maybe I don't give you any marks because I don't understand what is this circle. A circle doesn't mean anything. Right. Motor, if you draw motor, even if you draw motor also need a symbol inside like that. And then they got ear like this most of the time. Okay. So draw your symbols properly so that people can understand also. Of course, series, you just add the reluctance together. If you have parallel, as usual, parallel, we always use like R1 times R2 divided by R1 plus R2 if you have parallel circuits. It's normally what we use. The concepts here is just some assumption that we make in our calculation. For example, when we do exercise, if last time in the classroom, I don't really explain this. Okay, I assume that either you know or you go and read, or but sometimes the student will ask, for example, this one, they will ask how to take the length. Okay, so we measure the length actually from the middle here to the middle of the core here. This is the length for this core structure, the upper side. For the left side also, we all take in the middle here to here. Okay, because if you don't specify it as a mean length, we also can take here to here, is also correct. We also can take from here to here, is also correct. Okay, it's just the value will be smaller, of course, if you take the shortest length. Okay, and then the value will be bigger if you take the longer length. Okay, You can also take somewhere around here. It's also correct. Okay, but if you want to do like if you have computer lah, we can do like the iteration, so-called iteration. So we can calculate the exact reluctance of this whole core here. You take the whole of these things. You see how many lengths is there? There can be millions. Okay, so we want to take our life easier. We just take the middle. Okay, one length is enough. We're using hand calculation, not computer. Of course, if you want to do very accurate, you can do iteration. I can like integrate the length. Okay, using the width here or the length here to here. The higher, the longest length, you can do iteration, which you can use computer lah. 0 to x, let's say. Okay. L, then you have dx or something, you can do the total length. Okay, but we're using hand, so we just take the middle is sufficient. Did we go to this example in the video just now? Just now the video only stop here, right? So the next video will be all this example here. Okay, so again, we are taking the length in the middle. Okay, here, 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 and here, which you can see in the video later. So I'm going to play chapter 2C, which is the example part.
Example 3.
Okay, let me paste the link first. You can watch it on your own, and I will also project it here. There is also part D and part E lah. These two parts are theoretical parts only lah. So let's go to part C, the example.
We are given a cross-sectional view of a magnetic core with current I1 as 0.5 amp, current I2 as 0.75 amp, with the number of turns at N1 400 and N2 as 300. The relative permeability is given as 1000. Find the total MMF, the reluctance, and the flux of the core. As shown on the dimension, we have the length of the core given for the left and right, and also the top and bottom. We have a core depth of 15 centimeter, in which it will give us a square cross-sectional area of 15 times 15 centimeter. First, we need to sketch the equivalent magnetic circuit. For the source F1, to determine the polarity, we use our right hand rule and coil our finger following the direction of the current, and we will find the flux is flowing from the bottom to the top. While for F2, using the right hand rule, we found that the flux is flowing from the top to the bottom. Hence, the total MMF will be F1 plus F2, since the flux flowing out from each source is at the positive terminal. For F1, we have N1 times I1, and F2 is N2 times I2. We found that the total MMF is 425 ampere turns. To find the total reluctance, we have the length 1 on the left, length 2 as shown on the top, length 3 on the right, and length 4 at the bottom. Each of these core has their own reluctance values, and since they are in series, we can total them up, and we found that the area of each core is the same, in which it's 15 centimeter times 15 centimeter, and the mu is given as mu r times mu naught. Since the denominator are the same, we can simplify the equation to become total length divided by mu a, where the total length will be length 1 plus length 2 plus the length 3 and length 4. And we also can see from the diagram that these lengths are the same. Hence, we can further simplify to become 4 times the length of the core. One section of the core's length is half of 15 plus 50, and then plus half of 15 to achieve the mean length. And we divide by 100 to change from centimeter to meter. Hence, we get the total length as 2.6 meter. Substituting the length in, and the mu r is 1000, mu naught is 4 pi times 10 negative 7, and the area as 0.15 times 0.15 meter, we will get the total reluctance as 92 kilo ampere turns per Weber. After finding the reluctance, we can substitute in to find the flux, where is equal to the MMF divided by the reluctance, in which we will get 4.6 milliweber. Example 4, sketch the equivalent magnetic circuit and find the reluctances R, B, A, F, E, R, B, C, D, E, R, B, E, and then the air gap's reluctance. Also find the flux flowing through the air gap, the magnetic field density of the air gap, and also the intensity of the air gap. From figure 16, all the dimensions are in centimeter, and the cross-sectional area is a square. which means it is a 2 cm times 2 cm square area. And the relative permeability is given as 1200. From the diagram, we can see that the current flowing in is 10 amp. The number of winding N1 is 500 turns and N2 is 500 turns. From the first winding is connected to the second winding and the current flow is labeled as shown. Solution for example 4, we are going to sketch the equivalent magnetic circuit first. To start, determine the direction of the source F1 using our right hand rule. We coil our finger according to the direction of a current and the winding. We will get the flux flowing from the bottom to the top. Hence, the source F1 is labeled polarity as plus minus as shown. For F2, also repeat the same method. We coil our finger according to the direction of current and the winding. We will get the flux flowing from the bottom to the top also. Hence, we label plus and minus for the source F2. The reluctance RBAFE is in series to the source F1, so is linked together in series on the left hand side. For the right hand side, we have the reluctance RBCDE, which is series with the source F2. In the middle, we have the center core RBE series with the air gap reluctance. And it is parallel to the left and right core or the source F1 and F2. Flux 1 is flowing clockwise, hence we can label the direction of the reluctance as plus minus and plus minus. For the equation, on the first loop, we have the flux flowing out of the source F1 as a positive, and then flowing out from the reluctances are all negative. And also, for the loop 2, flux 2 is also flowing out from RBE and the air gap as a negative. Moving the equation to the other side, we will get all positive values. Hence, we get equation 1. Repeat the same method for equation 2 on the loop 2. Flux 2 is flowing counterclockwise. Hence, we also can label the reluctance polarity as shown. And it is flowing out from the source F2 as positive and all the reluctance as a negative. While flux 2 is also flowing out of the RBE and R gap at the negative on loop 2. Hence, we repeat the same for equation on loop 2. We will get flux 2 times all the reluctance plus flux 1 times RBE plus R gap. To solve equation 1 and 2, we can determine the MMF values and also the reluctance values from the diagram given in the question. Then we can solve for flux 1 and flux 2. The MMF can be found by multiplying the number of turns with the current. It is given N1 and N2 as 500 and the current is 10 amp. Hence, we get F1 and F2 as 5000 ampere turns. While the reluctance on the left core has the same dimension as the right core. Hence, they have the same value. Determining the length for the reluctance, BAFE, we can see that it's made out of 3 sections of the core, which is BA, AF, and FE, having the same length. Simplifying it, we can use 3 times the length of BA, which is half of 2 is 1, plus 50, and then plus half of 2 again is 1, which is 52 centimeter. We change it to meter for the length. And for the permeability of the core, we can use mu R times mu naught. Mu R is given as 1002, while mu naught is 4 pi times 10 negative 7. The area of the core is a square, hence is 2 times 2. We get 4 times 10 negative 4 meter square. Then we get the reluctance of the left and right core as 2.58 mega ampere turns per Weber. The center core RBE, using the length at the center, which is also 52, you can minus off the length of the air gap, or you also can directly use 52 since the length is very small on the air gap, and it doesn't make much difference in your final answer. Mu C times the area of the core is the same for the left and right core. Hence, we get 0.82 mega ampere turns per Weber. For the air gap reluctance, we divide the length of the air gap, which is 0.5 centimeter, change it to meter, and then divide by the permeability of the air gap, 4 pi times 10 negative 7. The area, we assume that is the same as the area of the core, which is also 2 times 2 centimeter square. We will get 9.94 mega ampere turns per Weber. Substitute the values of the MMF and reluctance into equation 1 and 2. We can solve for flux 1 and flux 2 by using the determinant method as shown using the matrix form to find the variable x and y. Or we can use the scientific calculator by pressing the mod 5, which is the equation, then choose 1